Good morning, folks, and student of the course 4006. Here we are. We're going to be trying to understand what happened when the information that you have comes in a table form. Like for example, here concentration milligrams per liter is being provided in this problem uh, within a table. So it is a function of time, as you can see here, but there's not a function. It's just a table. All right. On the other hand, flow here is a function. So we are used to integrate functions. There's no problem with a function. You can use many methods. If the function is very complicated, you can use any numerical method to do that integration. So the question here is to get the average concentration leaving this reactor. All right. And the average concentration, as shown here, is being provided by the integral of a new function, sort of like the flow multiplied by concentration, and then divided by the average flow. So you have this sort of like the average uh, flow, or the average mass, so to speaking, divided by the average flow. So with that said, we just need, as shown here on this formula, we just need the average of Q multiplied by C. All right. And so let's work that out. How we work with data that is in a table form. Okay, first of all, let's take this information into Excel, which is right here. So I have that information there. And I also need, for example, I also need Q for getting this the way I want. So let's plug here the function Q, and Q is a function of time as well. So what we need to do is get this here, and the next part will be like getting Q times, let's put it like this, and that will be Q times C also of time. Now, so what we're going to do is let's get Q first of all. So we write this equation down here. That would be the flow. That would be 20 plus 10 times the sine of 2 times pi. Let's get pi there. Divided by 24. And that has to be multiplied by t, which is come from here, minus 10. Now, close those parentheses. That would be 1 and 2. Enter, and we have that flow. The flow meter cube to the over second, and you can drop this down until the hour 24, and that's it. So you got the flow. Now we need to get this function equal, and this time this, and you can again drop this down. All right, so we are ready. Now here's the tricky part. If you want to use like a conventional Simpson composite method or trapezium method for a particular n value, it might happen that you will not have the value that you want to do this. So in other words, you might not have, like for example, there's a big jump between 1 and 5.5, so you're gonna miss, like for example, if you said that n is 24, you're gonna miss a lot of values. Like for example, from 10, 11, 12, you're gonna miss 11, and from 20 to 24, you're gonna miss 21, 22, 23, and that's kind of hard, particularly for the C part, because the Q part is a function, so you get those numbers easily. But the C, you will have to do interpolation. Now the question is, will that really improve your area under the curve, this curve? Because this curve will provide, if I integrate Q and C, that will provide this numerator here. But will that improve your result? and let's take a look at it. Let's plot for the time being. This will be time, and let's plot that with this one, right? So let's insert, and let's do this, and let's do one of these, because that's what it looks like. All right, so here we are. Let me sure that I'm plotting the right thing, because sometimes you things get messy. Select data, just to want to be sure. Edit, and what I got on the X, yeah, is the column A, and what I got on the Y is the D column. We are perfect. We are right on. Let's say okay. Now we got this chart here, and this is what I was saying. Do you really think that by this big jump that I have here from 10 to, I would say, 14, I need to improve this side a little bit better so I get a better picture of it. Everything is right here. Everything, just to get this right, let's do this. Let's add labels. There we go. And then some of these labels are kind of one on top of the other. I can move it around so it clearly show where that come from. And that's it. All right, this 15 come from the 0, and this 19 come from here, and so forth. What I was saying is, will you think that you will improve by having a large N? And the answer is no. You will not improve this data because it's not really a curve. It is composed of a small straight line, like for example, this straight line, this straight line, this straight line, this up to here, and from here to here, and from here to here. So you, to get the area under the curve, you might as well use a trapezoidal rule, obviously, but within that section. So you will be adding this area, this area, this area, and so forth. And you don't need to, fuss too much about it, because the area will be as perfect as it can get. Let's do that. So by saying that, what I'm saying is, like for example, we are right here, and we want the area between here and here, right? And so that area under the curve is just the definition, the trapezoidal rule, that will be equal to the sum of this plus this divided by 2, and that need to be multiplied by the difference of this minus this. Oh, sorry for that. Let me fix this. A5 minus this one out. There we go. So we got the first. Let's table this like the area. So we identify that column as area. Now I have that first area. That's perfect. That's what it is. Now for the second area, we need this and this, and the difference will be between this one and this one. So what I need to do is just drop this. See? That would be the difference between, let's get inside here. As you can see, is the average of the elevation or the height, 24 plus 19 divided by 2, multiplied by the separation between 5.5 and the 1. And that will do. For the next one, you keep moving, and you keep moving until you get to the last one. And the last one here will be, let's check this one out, is the average between this high, 75, and, oops, I missed the other number, there we go, between 75 and 18, and multiplied by the difference between 24 minus 20, and that will be it. So I got pretty much here all the area, and that's area under the curve, and that one is perfect because it's by definition of the trapezoidal. When you have, like for example, a trapezoidal figure here or area. So what I need to do is just add all those areas. So let's use sum. And that's it. and that's the area under the curve for this curve. So I don't have to do interpolation at all because it's not required. There's no, you are not gaining anything by splitting, for example, the distance between here and here because you want to, because that would be two trapezoidals when you can use only one to get that area under the curve. So it's not really required just to do that. So I got this area, and that area is by definition the area of the numerator here. Okay, that's the area of the function qt times c of t dt. Now we need the area for the flow. Let's area here, that will be q times c. Let's get capital Q times c. And now let's get now here, let's move this a little bit to the side, and let's get the area for Q. The area for Q, I mean, you can, it would be straightforward. You can get how you want to do this. Now, Q is truly a function. And I will say for Q, you can now benefit from having a large value of n because it's a function. So let's work that out. How would that look like? I can certainly use this here because that's what it is, but it is a function. Since it is a function, I can certainly do an integration for that particular function instead of doing, in fact, we can compare. We can definitely compare what will be the area by doing like trapezoidal, small trapezium, in the integral of small trapezium versus the true integration of this function, which will be this one here. So we can certainly do that. Let's do the first one. Let's do this area under the curve and see what will happen here. It will be the same pretty much as we did before, except that we pick this one. That would be this one plus this divided by 2, and that multiplied by the difference of this minus this. And so if I do that, the next thing will be just to drop this down to up here, and that would be the area under the curve for the flow as an approximation, because this one is truly an approximation, because basically it is a function, and that's what I want to make a big difference. One thing is a function and another thing is a table. A table is the way it is. The data and that comes from this table cannot be improved anymore to what it is right there. But for a function, you can definitely improve the area as n get larger and larger and larger. So let's get the sum here, which basically will be like moving this to the side, and I got that. So the C average for this problem approximately will be this value, which is true, is a true value, but this one is an approximation. So that's what you get, 3.44, and that would be sort of the average value between the two areas. Let's see if we can improve a little bit more the area under the curve for this function. You certainly can do many things, like for example, you can apply truncation error and establish what would be the value that you want that area be exact to a given number. I will not do that. That will be a separate subject. What I will do is pick different value of n and see how well or how well I get to this area that is shown here, and or how much I depart from this 486 value. All right, let's do that. Let's say I'm gonna copy this. Actually not, because you know what? Let's copy what I need to copy here is to be sure that you understand what I'm doing, is the value of A, we know that we're starting on 0, and the value of B is going to be 24. I'm going to be using trapezium. So let's say that N, for this trapezium, I can pick any number. Let's pick, sorry for that, let's pick, I'm going to pick 24. Let's pick 24 and see what happens. So now, the dt for this problem will be this minus this divided by this. So obviously we are picking a delta t of 1, and now let's work the number that will be t, and this will be the flow. All right, so let's see. For t, we're gonna start here, and we're gonna be increasing this by the calculated dt value, and let's put a dollar here. So obviously if I drag this down, you see the number increasing as should be. Now for flow, actually for flow I'm gonna do this. That formula is already written here. How about if I pick it from here, copy that, and now let's get here, drop it there, and let's see, instead of A4, it need to be pick A24. That would do. And perfect. Obviously when it's 0 is 15 as above. But here's the part. I don't know, 2 is not in the table. Let's see. You see, 2 is not in the table, but since it is a function, it will be calculated. No problem. So let's see. And now let's go. Let's get this to 24, which is what I need. A little bit further. 2 more. That's it. All right, 24 obviously is what the number that you show here as well. So no problem. Here we are, and let's fix this so it looks much better. Actually, let's get this to here and centralize everything. You want to put borders in everything. I don't need this column. All right, but that will be good enough. Now I got T and I got Q. Now the area will be gonna be applying trapezoidal area under the curve for n value. In this case, n is 24. So if you remember, the formula for this is equal to before that, let's put area here, or trapezoidal area, so we know what we're doing. So that would be, the first one is obviously will be the same one, but here's the trick. Everything in the middle has to be multiplied by 2. So you take this number and drop it almost to the 24, 23 here, and this one will be like this. Now what I need is the sum of everybody there from here to here. Whoops, missed that one. I don't know what happened. Let me fix this. From here to there, and let's be sure that I got everything. 48 and 24. Yeah. All right. So now take that nice 60, and this is the part. You need to multiply that by delta x. We know that is 1, but I like to write it like down, and that divided by 2. That's 480. So let's see what I got before. No bad, 486. See what I'm saying? It improved because it comes from a function. Now, will that be okay? 480, would that improve a little bit more? If I get the analytical solution of this, I will check. You can definitely get the analytical solution of this, but since we are in numerical method, let's work out with numerical method, because that's the idea, right? Let's get this better, actually. So what we're gonna do is we're gonna copy this up to here, control copy, and put it nearby here. Let's say I put that right here. Now, instead of 24 of the n value, let's get 100. Now that we're into it, n equal 100. That's a lot. I mean, definitely, I believe that this will be better. If you don't believe me, how about 200? Let's get 200. That's it. You want more? Now, I leave it like that because I need to drag this table long enough. So let's be sure that everything looks good. And this had to be multiplied by 2, and so for this one, except the last one, obviously. When I hit the 24 on here on the time, you don't need to do anything else. Let's check this one that is looking good. G21, yep, G21, perfect. So we drag this down a little bit until I hit the 24 on the time. So that's gonna take a while. Let's see how we're doing. Whoops, I think that I overdo it. Sometimes that happens. Oh, here we go. All this you just clear. You got that content. All right, and now what I need is the sum equals sum. Actually, before that, let's fix a few things here. This 30 is not right. That you don't have to multiply that by 2. That's it. Now we are talking. So we get the sum from here to here, and that need to be multiplied by delta t, which is right here, divided by 2. And let's see what number I got. 480. Let's see if I can, there's anything hiding there. Wow. Nope. It looked good. I mean, it seems like that's the analytical value. No decimal places, nowhere. So, and that was with what? Let's see. I hit the 480 with n equal 24, but there was no improvement going from n equal 200. No improvement at all. So what that tells us is it seems like the analytical value is about 480. Let me work out the analytical number and I'll be back. I want to be sure what is the analytical value for this, just to ensure that that's it. It's kind of strange that I don't see any decimal places, so I'll be back in a second. So let's work this integral here, this part here, but now let's do that analytically, because that was kind of funny. I got the 480, that number, and so like when we try with n24, then we try n200, and it hit the 480 mark. It's not moving at all. So let's do a check on the analytical part and see whether that makes sense. So we want to integrate this function as part of this here. So it's an integral between 0 and t, and this t is 24, of 20 plus 10 sine of 2 pi over 24 t minus 10. Close that up. So, and that's dt. All right, that's this with this, this with this. Let's put another one here, and that would be dt. Right, so we're going to break this integral in two parts. So that will be the integral, the integral between 0 and 24 of the 20 dt, plus another integral that will go from 0 to 24, and that part will be for the 10 sine of 2 pi over 24 t minus 10. I see. Interesting. You can quickly tell that eventually you're gonna get, like for example, if I integrate this part here, so you got 20t evaluated between 0 and 24, and if I continue this part here, that will be like 20 times 24, so that's 240 plus 240, that's the 480. So you get the 480 only for this part here. Interesting. Only for the 20 dt. So what that means is that somehow when I integrate this, there's going to be an area positive and an area that is negative, and when I add both together, they should be 0. Because I mean, I see the 480 now, which is coming for only from this part. So this part, I guess, well, let's work it out. Now, so I mean, be sure that you understand what I'm saying here. That I kind of quickly go ahead and do this part because I was interested to see where the 480 come from. Now let's check this out, if this is really truly add to 0. Kind of funny here. So the integral of a sine, let's say this would be plus 10. The integral of a sine is cosine, and that would be a negative somewhere here. And through what I have internally here, that would be 2 pi over 24 t minus 10. This with this, another one, divided, let's see where I put everything, divided by, in this case, that would be 2 pi over 24. And that needs to be evaluated. This plus is kind of weird here. Let's put it somewhere here. Okay, plus, and that would be evaluated between 0 and 24. All right. If I do that and simplify a little bit, let's see. 10 divided by 2, that would be 5, and 5 multiplied by 24, that would be negative 120 over pi. And what I need to do now is evaluate cosine cosine of 2 pi, let's see, over 24 t minus 10, this with this and this. Now I need to evaluate that between 0 and 24. We are almost done. Let's see, I'm kind of curious. This has some periodicity, so it means that somehow the one area is identical to the other, but with a different sign. There's a negative here, so let's work that out. So that will be minus 120 over pi by the cosine of 2 pi over 24. T, that would be 24, so 24 minus 10, that would be 14. Close that one up. This with this and this with that. All right, and that would be minus, but I have a minus here, so minus, well, whatever, you understand what I'm saying. It's minus 120 over pi cosine, oops, that's ugly, cosine of 2 pi over 24. T minus 10 in this case is 0, so that would be minus 10. There we go. All right, so let's get a calculator to check that out. But it looks like, yeah, this part here might end up positive. This one might end up positive, and this one might end up being negative somehow because of that negative there. Here would be positive, but with that negative will end up being the whole thing negative, and this has to be positive. Well, that's what I think. Let's copy this. Again, I mean, this is sort of like I'm dropping through a tangent here, just because it is a function. I mean, the Q was not given in a table, was given as a function, And as a function, I should be able to integrate it either analytically, if it's one of those easy ones to integrate, or numerically, but with a large value of n. What surprised me here on this integral was that the fact that I did n24, I did n200, and they both give me 480 without any decimal places at all. So that's what kind of triggered me to go to, now let's do analytically and figure it out where the 480 comes from. And I you know, it seems like it's only from the first part of the 20 that 480 comes from. So that means that all this part here of all this sign stuff has to be 0. I mean, when you add it together. And that's what we're going to find out. Hold for you a second. Let me get my Excel spreadsheet here just to get this stuff done, or a calculator, but I will use a spreadsheet. I will use Excel for doing this. Hold for 1 second. So I'm here in Excel. Let's figure it out whether that really makes sense. I'm very curious. You can certainly plot this curve and figure out yourself that it must be 0 somehow. So, but I mean, these are the true number from the integral. So we're gonna check it out. So let's see. The first one would be minus 120 divided by pi times the cosine of parenthesis here. That would be 2. I can simplify that, but leave it the way it is. Divided by 24, and that has to be multiplied by 14. Oops, not 13, 14. And I close the parentheses. And I think that will do with this one, and I guess that we are ready. Aha! See? Change sign from negative, change to positive, so that means this part is negative. And so that's the number, huh? Alright, I can use pretty much all these to get this number, except that I need to change something here. Let's see. I got the negative, alright, 24, 24. And the minus 10. So I only need to change this number here to minus 10. And now be careful here, because I mean, this negative and this negative, that will be positive. So I gotta get this negative out. Oops. And that will do. And this negative, I need to close the, let's see, this parenthesis, I have to do with that, and I need another one here. So there we go. That will make sense. So I got what? 0797. Oh, all right. I'm missing another. Let's see. More decimal places here. Oh, I see. They're identical. So let's see. Well, let's do the sum of them the way they should be. And yeah, that's it. That definitely did it. So in other words, this part here is definitely 0, no question asked. And with that said, then now we can return back to our original spreadsheet that we were working on this. So we are back here to the original spreadsheet. We demonstrated where the 480 come from. Kind of weird. I said no decimal places. Something weird is happening. But anyway, we demonstrate then that the integral of these, if you use the table only for a function, that might provide, you know, that give you some error. So I mean, from 486 it dropped to the true value actually of 480. So I can recalculate it. I can recalculate, sorry, the C average by using the correct value for the area of the flow, the average. This one cannot be corrected any further, but because it comes from the table, and the table is what it is. So the only thing that I got some correction was on this one. So the average value finally, I can plot it right here. Let's say that this stayed the way it is. Let's see. Let's open few spaces here to get this elegant. Insert. We can insert a few more columns. Insert. One more. Insert. And the true value now, the C, the most I would say the most correct value, because actually, why I'm doing this is because it's a use the best numerical integration method, right? And that's true, and that's only true for the function, because for the table, I mean, it's the way it is. That you can I'm using the sum of many trapezium because that's as perfect as it can get. Now, for the function, that's another story. The function, then the argument here is that definitely can improve as n gets bigger and bigger and bigger. The only interesting caveat here is that I did the analytical solution, which just happened to provide the 480 as well. So let's see what the new C average is. That's right here, C average, and again, what would be this value, which is the correct value for the table part, that divided by the 480, which come from many places. And let's see what we got. That's it, 3.48, and that would be milligrams per liter. And so this one. All right. So this again, big, constricted within the table. And this one, if you split, like you integrate the table part, but then you correct the function part, and that provide. But they're close. I mean, it depends on what. Remember, some of these, like for example, here they're talking about a reactor. It could, I mean, I'm thinking more like when you do water treatment. You do water treatment, and you have to, and the outflow is going to the coast. There's some, I would say, very stringent the amount of contaminant that you can put to the coast. So that by what I'm saying is, it's very important to get this number right. Thank you. I really appreciate you watching this video. Again, it's just an explanation that sometimes data is not always a function. Like for example, you can have this Q value as well as a table within a table, and that will be like, as I did here, like this part here. But if it comes as a function, oh, perfect. Life is beautiful when it's a function. Again, thank you. Be safe, whatever be your final destination. Bye.
We interrupt this program to bring you a special report.
As always, there's more into it. I forgot to mention something that to me is very important. Is the fact that you definitely can improve the area under the curve for QC, not for C. I just want to be sure that C is from the table, it's the way it is. But since you are multiplying or creating a new function, which is called QC, if you improve Q because you have more points, you are definitely improving this function, Q times C. So that's very important to understand that. If Q comes from a table as well, then there's no point. I mean, that's the way it is. This comes from a table, the concentration, and so Q. But in this case, Q is a function. Since I need to properly integrate that between 0 and 24, the whole thing, Q times CT, can benefit from a proper function. And so you are not, let's say, for example, if between 1 and 5.5, you want to look for the other numbers that are missing here, you can look for them. I mean, you are not improving your data. It's just you are completing the table. That's all. But in doing so, you improve Q, the area. I mean, the function, the total function QC. That's what you're doing, improving that new function. All right. With that said, I did that, and here in result 2, and let's see if this moves. There we go. I did N24, as you can tell. I mean, there's a lot of value here that are missing. All these values that has a lot of decimal places probably come from interpolation as well. And that come from here. from the original table, you interpolate and you get what every value is missing. What is important to say is that you are improving QC, not C, but the whole new function that you're trying to integrate, which is this one, Q times C. With that said, if I go to the bottom, you see 1649 versus 1672. So it definitely improved the area under the curve for the new function called QC. If I do all the calculation, the 480 will not improve at all because we demonstrated that at 24, the area under the curve for the flow, this one here, the average flow, will be 480. So the C average is finally 3.43 or 3.44 at 2 decimal places. If we go back here, that is either by using this formula here, 344, which is kind of interesting, right? Because here the Q and the QC and the area was done through the table, and that was 344. If we try to improve only the function, the average flow, but not the QC, you get 348. But the truth of the matter will be this value here, 3.44. Interesting, huh? Because it's basically we go back to this result. All right. Well, that's it. Now I'm leaving, and this is the end. I hope. Bye.